All right. So we are gonna go with the homework assignment. So did you guys mostly get the assignment done or okay, cool. All right, excellent. So do you still want me to go over the assignment? Okay. Let's see, I'm not. Okay, cool, cool. Not- That's all good. All right. So as I go through this exercise, you guys can tell me what your main struggle was, okay, and what you learned in the process. And I think it is good to write down exactly what you learned in the process. Okay, I made this mistake. Okay, or I mistook this concept with that concept, or I missed this one instruction, because all of those are super important concepts. Okay, this entire homework assignment was me getting you guys to study for the final exam because instead of debugging my code, you're debugging your own code, and in the process of debugging your code, you are basically saying, okay, how do I get this done? What is the C statement doing, and how do I translate that into assembly code? How should the stack be set up? What should be in each register, and so on. So that whole exercise is essentially studying. All right, so we will go ahead and take a look at the C code on one side and then the assembly code on the other side, like so. Delete. There we go. All right, so on the left-hand side, we have the C code. On the right-hand side, we have the assembly code. And the function is function f. It returns a pointer to a struct node. And we need to define it somewhere here. And that's where the halt instruction is. The main program is already supplied, or the main function is already supplied. You just have to implement function f. All right, so are there any questions that I need to address before we work on the code here? No questions? All right. All right, so the first thing we probably want to do is to figure out what should be on the stack, okay? Because without a map of what is supposed to be on the stack, which location is supposed to be what value by the time you get to function f, it's pretty hard to get it to, it's really hard to debug it. So what we'll do is we're going to take a look at the C code first, okay? And then we'll take a look at the matching, assembly code. So in the C code, we have a p first, which is a pointer to a struct node. In the assembly code, we allocate 1 byte for p first, okay, which is appropriate, and which is just a pointer. And we also call main from the entry code, so we have 1 byte sitting on the stack already by the time we get to main, which is the return address from main back to the entry code. So I am going to start with the usual things that I do, which is to create a spreadsheet first. So let me go to Drive and then go to the folder. Okay, this is CISP 310. Go to the shared folder, which means whatever I work on today, it's already going to be in the spreadsheet in the shared folder. This is going to be a Google Sheet, just a regular one is fine. Get rid of this. 2025 1203, and then we do the usual stuff. Okay, and this time it's gonna take. We'll give it a bunch of locations here. Deck to hex. Oops. There we go. All right. So we already know what column C, or what the value is, but we also know what the row is. Okay, this is the return address from main to the entry code, and then we look at the actual starting point. Okay, we look at the beginning. So that is going to. It doesn't even have an initialization of the stack pointer, which is okay. Um, it's going to be 7, I think. All right, so we'll put a 07 here. It is 7, right? Yep. All right, so the return address is 07. The next byte below that is my local variable in main, which is what, P first? I can't remember the name. Yep, P first. So P first of main, and it is uninitialized to begin with. And then we go back to the C code. We should have it initialized to a 00 after that. Okay, so that turned into 00. Oops. Uh, I want to make it look nicer, so we'll do a quote 00. There we go. And just kind of make these columns a little bit more compact. They don't need to be this big. All right. So now we are down to the first function call. We are calling the function with the address of n1. And then when we look up n1, n1 is a global variable. So the address of n1 is pushed and then followed by the address of p first. All right, so when we're pushing, this would be the address of um, n1, serving as the second argument to the function. And I'm just looking at the name of the parameters from the function's perspective. So pn is the name of the parameter. So this is Pn of the function f, and then this is going to be Ppn of function f, and that would be the address of p first. So we know this should be fe, and then for this one, I have to assemble the program first before I can find that out. So we'll go ahead and run with a spider. So we'll run this. This is ar.ttpasm. All right. So the first thing we do is not even to go look for the trace. Instead, and I don't know where my assembler is. Okay, where's my assembler? There we go. We go to the assemble tab. We look for N1 because I need to know what is pushed on the stack. Is that correct? So this is N1. N1 is a label for the location 0C. So I go back to my diagram and say this should be a 0C. Okay, so at this point of time, the stack pointer should be pointing here at the halt instruction. And that should be what I should be seeing on the, by the time we get to the halt instruction. So now we can switch back to the assembler, go to the analysis tab, kind of look up, what locations got what value. Location FF got a 07. Location FE got a 0. Location FD got a 0C. Location FC got a value of FE. And this is the return location. I forgot about that. So let me put it here. So this is the return address from F to main. And the stack pointer should be pointing here. Get rid of that. And we'll just put question marks here because that's not really super duper important. Okay, so everything is accounted for, okay, because we just saw all the memory overwrite, and it is consistent with what we think should be happening. And it is also helpful if you want to look at things from the perspective of frames. This would be the frame for main, okay, the return address and the local variable. That would be the frame for main. I'm going to use one color here. This would be the frame for the first invocation of f, at least up to this point, okay? If it has local variables, then it's going to have some more items. But at this point, we know there are two distinct frames, one for main, one for the first invocation of f. Are we okay so far? Okay, very good. So now we switch back to the code, and then we go, okay, now that we have verified everything is on the stack, is correct, now we start to deal with f. F does have one local variable called result. Okay, so we're going to say, okay, result has an offset of 0 from the base of the frame after everything is allocated. F underscore LVS is going to be the offset to the last local variable plus the size of the last local variable. Result is a pointer to a struct node, so it only takes 1 byte. Every pointer is just 1 byte, okay? So that's why we do this. And then we also need labels for the parameters. So we have ppn, that would be LVS1 plus, because this one is accounting for the return address to the caller. That's what this one is accounting for. And then f.pn is going to be f underscore ppn 1 plus, because this is a pointer to a struct node, which makes it still a pointer. So that means it only takes up 1 byte. So these are the offsets to various items on the stack. And then we have to remember to allocate for the local variables. So we have an LDI. I use register B because I don't want to mess around with register A unnecessarily, especially when the function has a return value. So with LDIB with F underscore LVS, subtract that much from the stack pointer, and then remember to undo this afterwards. And then we do the usual return code, which is LDBD, increment D, and then JMPB. Put that halt instruction somewhere else. And we can always stash it somewhere here. All right. So this is the entry code done. Okay, the exit code also done. So if you don't want to do anything else, you can just kind of run this to make sure that the program does terminate correctly. Okay, even though it doesn't do a single useful thing, it should still terminate. Okay, so that's something that we can do. Okay, so we can take out this halt instruction just to run this code to make sure that it does terminate. So we'll go ahead and just run this by itself. How many people use GitHub in this process, or at least the Get utility program? Okay, for 400. Do you find it useful? And which part of Get do you find most useful? hmm So did you use the diff feature, like you're comparing your current code with the last time you check in? Okay, yep. So that would be the proper way to use it. Cool. So we do terminate the entire program with the stack pointer back to location 00, and we're using the correct halt instruction. So we know the entry code and the exit code are working okay, even though the function doesn't do a single thing. Okay, okay, that's fine. Because it is important to test the program incrementally, and that's kind of what I'm doing. All right, so now that we know that code is right, I would check it in to get into get right away, just to make sure that I have an understanding that the entry code is working. Okay, the entry code would be everything from line 22 to line 28. The exit code is working, which is everything from line 31 all the way to line 36. So that's a good start. Okay, now we go into the actual code, and we have straight away we have a kind of ugly condition to evaluate, which is on line 16. So line 16 is an or condition or a or expression. So we have to evaluate each one individually. If pp if what ppn points to is null, then I go straight to line 18. If what ppm points to is not null, then I have to evaluate the right-hand side of the disjunction. If that is also true, then we also go to line 18. Otherwise, we have reasons to go to line 24. Okay, so that's what we'll do, is to kind of do all this stuff here. So we'll start with the right-hand side, or excuse me, the left-hand side of a disjunction. With disjunction and conjunction, you don't have a choice. You have to evaluate from left to right. If it's addition, subtraction, or whatever, you can evaluate in any order. But if it is a disjunction or conjunction, you have to evaluate from left to right. Okay, So I look at the rest of this code here. It looks like it'll be kind of nice if I keep whatever ppn points to because I need that over here. So, okay, so we'll do that. So LDI, at this point I can use register A, B, or C. It doesn't really matter. Um, so we LDIA with F underscore ppn, add AD, that would be the address, and then do LDAA, that's ppn itself. LD, I think we can do another AA. So now register A is whatever ppn is pointing to. Yep. Yeah, that'll work. Yep. Yeah, I don't see why I need to save a register at this point because the second half of the disjunction still needs to depend on whatever ppn points to. It doesn't depend on ppn itself. So that means there's no particular reason why I need to save it at this point. Yep. All right. So register A now has whatever ppn points to. So now I can do an AND AA. But this time the JCI is going to go to the then portion of the conditional statement. So I'm going to say F underscore then 0. And now I might want to finish up the entire thing. So there's then, and then there's else, there's and if. At the end of the then statement, I really need an unconditional branch to end if to skip over the else portion. So when I write code, this is the way I do it. Okay, I write the entire structure out, and then I go back to specify, okay, what do we do when we are at the then portion, and what do we do when we get to the else portion? So I backfill those segments later on. Okay, so the JCI says, okay, if whatever ppm points to is null, we go straight to line 18. Otherwise, we have to evaluate this kind of messy thing here. It's not super messy, it's just a little bit messy. Okay, we already have whatever ppm points to in register A. It is serving as a pointer to a structure, and we need to access the member called value of that structure. So that means now I have to use another register, say register B, to store the offset to the member called value. So that would be node underscore value. And then we add those two. So whichever way we add should be okay right now. I don't need to save register A. Maybe I want to save it. Okay, I'm just looking forward a little bit here. Yeah, so maybe we want to save register A. So I'm going to use another register, which is register B here. So what register B is the address of the member value of a structure that is pointed to by a pointer, which in return is pointed to by ppn. Okay, so being able to spell out that whole thing and articulate it is really important. It is not only for this class, okay? It is also useful when you move on to CISP 400 if you have not taken 400 or the CISP 430. Okay, being able to read a statement and understand exactly what it means, okay, is important. All right. So that is not what I want to compare because I need the value of the member. So I just need to do another LD. So we will do a LD. We can destroy register B. So register B is now the value of the member called value of the structure that is pointed to by a pointer, which in return is pointed to by ppn. Okay, so I can articulate it because I can actually visually see the whole thing in my head. No, I actually don't visualize. I actually understand the logic of it, but not so much the visualization. So if you are a visual person, you might want to draw a picture. Okay, so that means here is the value member of a structure. Okay, I don't know exactly where it is, but I know there's a member called value. It is a structure that is pointed to by a pointer, which in return is pointed to by ppn. Okay, so being able to draw that picture is important. Okay, because now when you get to this line, you can now say, okay, what am I supposed to be looking at here? So what is ppn? Ppn is a parameter that is sitting on the stack. So it has its own offset from the base of the frame, and the base of the frame is pointed to by the stack pointer, blah blah blah, and so on. Okay, so well, let's see. Okay, what else do we need to do? I have the left-hand side of the greater than. I need to figure out the right-hand side of the greater than now. So we'll go ahead and do that. Okay, so we'll use, we can now reuse, we can use register C for sure. So we'll use register C, LDI register C with, hmm, I might run out of registers anyway, so F underscore PN, that's the offset, that's the address of PN. This is PN itself. And then we need another register to store the offset to value. And we cannot use register B over here. And we thought that we want to save register A for later on because we need it back here. But since I'm out of registers, well, it's okay to refigure that out if I want to. Hmm? You mean here? Oh, because register B would still be the same. But then I still lose ppn or whatever ppn is pointing to. I don't want to lose it. Okay, so now it depends on how you want to complicate the code. One thing I can do is to save register A on the stack, use it for whatever I need to do here, and then pop it from the stack. So the trade-off is the code involved in pushing and popping more expensive compared to recalculating, what I should have in register A? The answer is I think it's a break even. Okay, so that means I really should not be wasting my time doing a critical optimization when it doesn't buy me anything. Okay, so I'm just gonna go like, oh, okay, fine, we're gonna destroy register A, and then we'll figure that out again, later on line 18. I mean, that's just the way it turns out, right? I mean, what you said, would save me from reloading node value into the thing. So this is node value, not f value, because it's a member. Yeah, there are many ways to do it. I mean, yeah. So now we have the address of the member of the structure the PM points to in register A. Need to do a dereference. Okay, so now we have the value. So now we can compare register B with register A. The question is, in which direction do I want to compare? This is a greater than, so you got a few options here. You can do a CMP um, AB, and you can do a J. Okay, so JCI versus JLI depends on the signedness of the value, and I cannot remember. So we'll go back and take a look. It is unsigned. Okay, very good. So since it is unsigned, we're going to use JCI to the then portion because this confirms that um, PM points to value is less than uh, whatever ppm points to value. So this would go to the then portion. This would go to f underscore then, and then the jmpi over here is going to go to else 0. Okay, so that's one way to do it. There are other ways to do it too. All right, so at this point, I'm going to put a halt instruction here because I think I have written enough lines of code to probably time to debug it first. Okay, at least to confirm whether it's working or not. So I'm just going to say then of f, okay? And then we put another halt here. And the comment is this is else of f. Okay. So now I need to actively design the caller to test whether this is working or not. Okay. based on how we initialize P first, it should go to the then portion because ppn is the address of P first. So when we dereference ppn, it becomes P first. P first is pointing to a null character, or it's a null pointer. So that means the left-hand side of the conjunction should be true already in the first invocation of function f. Is that okay? Does everybody kind of follow what I mean? Now, you can also see that from the picture that we have on the stack here, because we already know the ppn is a fe. Okay, it goes to fe. Fe itself is a null pointer, so that satisfies the left hand side of the disjunction, which means we should go to the then case already. Is that okay? All right, so we are going to test the code to make sure that at least that part is working. So make sure that we save it first, and then we go to River Spider, test run it. All right. So now we go back to the assembler, go to the trace. Yep, we ended up in the then portion, and we are using the correct JCI to end up in the then portion. So that's all good. Okay, so right now we know this part of the code is working. I cannot test the second or the right hand side of the disjunction yet because the left portion is already true, so we never exercised the right hand side of the disjunction. So what I would do in my code is to mark it and say that we haven't really tested that portion yet. So we're going to say uh, the following right hand side of the disjunction has not been tested. Just a note to myself so that when we succeed in the first call, the second call would exercise the second portion. Okay, so I just want to leave a note to myself. All right, so what do we do in the then portion? This is all we need to do. Okay, so I think line 18 to 20 is tedious, but it's not conceptually very difficult. So we just have to go like, okay, we'll do one thing at a time. Okay, LDI, register A with F underscore PPN. We have to recompute the whole thing. We get to the address of PPN. We get to PPN itself. And then we get to whatever PPN points to. And this time I save it in a different register because the next line needs the L value, which is what we have in register A in this case. So I would try my best not to destroy registers unnecessarily. So now I think I might run out of registers again because I only got one more register to play with. Darn. Okay, that is not gonna work. Do you see the dilemma? Okay, what I'm trying to do is to say since we have the address of the right hand side already computed, we have the value of the right hand side also computed. The the address of the right hand side can be reused over here, but I don't have enough registers to put it. So unfortunately, that is not going to work. All right, fine. So register A is just the right hand side. I'm not reusing the registers. So now we look at the left-hand side here. So the left-hand side, I cannot reuse register A, but I still have register B and C, which is more than enough. Just enough, I should say. So this is a PN. This is the address of PN. This is PN itself, which is a pointer to a structure. And then this is the offset to the member called pnext of the structure that B is pointing to right now. And now we have the address of the member pnext of the structure that Pn is pointing to. Now we can do the store. There we go. All right. So I just did a whole bunch of code here. I'm going to put a halt instruction here. Okay. In other words, we want to figure out, okay, am I doing this correctly? So now we have to figure out what should be the side effect that I should be able to see. So ppn, or whatever ppn points to, is a 0. So we should be changing N1's P next member to a 0. Okay, so I'll just document it here. So we are now saying, N1 dot P next is getting a 0. Okay, because in this particular function call, the first call to the function f, this should be the side effect that I should be able to see. All right, and we put a halt instruction here, and then we just go ahead and save the code and run it. Does anyone feel that you now know more about C programming than at the beginning of the semester? It is a good side effect. It is a good side effect. All right. So we go back to the trace, we go all the way to the end until we get to the halt instruction, and then we ask, is that the P next member of N1? Okay. So what we can do now is we go to the assemble tab and we go like, okay, it is the first member of N1. And we now look at the code and ask, is the first member P next? Because I really cannot remember. Oh, wrong. Wrong place. Sorry. It would be in the C code. Okay. Because I need the C code to be consistent with the assembly code. So P next is in fact the first member. So I just verified that by the time we get to the halt instruction, it is correct. It did the right thing. Okay. So now we can move on to the next line in C++, which is we need to retrieve whatever pn itself is and then use it to overwrite whatever ppn is pointing to. Okay, so we can do that. So that one is less complicated. Okay, you just do a LDI f underscore pn, register a f underscore pn in the C code. Give me a sec. Yep, there you go. All right. And because I'm using VI, all of those things, switching between the pane and moving the cursor around, they only involve the use of the key, only the keyboard area. I don't even need to use the mouse at all. And guess what? When I do need to use the mouse, I don't have to move my hand either, because my little mouse control thing is right here. This is this is the best keyboard for programmers who use the keys a lot, especially in VI, because in VI, the whole design philosophy of VI is do not move your fingers, which means it's useless to my son. How does my son type? He only needs 2 fingers. I I looked at how he write programs. I mean, he's a computer science student, so he go like that. I go like, wow, okay, that's a whole new level of user interface that I am not familiar with. I need all my fingers on the keyboard. He only uses 2. So, right, okay. So we need to calculate the left hand side, the right hand side. Okay, this is the offset. This is the address. This is the actual right hand side. And now we need to figure out the left hand side. BF underscore ppn. That's the offset. That's the address. This is ppn itself, which is also where we need to store the right hand side. So we just do a stba, and that should get the job done. Okay. But I'm gonna check it, okay? Even though it's only like what 7 lines of code, I want to check it, okay? Because I have what it takes to check this code. So that means by the time we get to this particular halt instruction, what we should be changing is p first is actually p first of main. Okay, let me emphasize, p first of main, which is pointed to by ppn, is what is, huh? In reverse order? What do you mean by PN is on the right hand side, and then PPN is on the left hand side. Yeah, the first one is done already. We verified that one too. Yeah. So for the second one, which is line 19, we are overwriting p first of main using pn, but we also not know what pn is. Pn is just n1. This is the address of n1. Okay, so I write all the comment here. So by the time we stop at this halt instruction, I can double check. Okay, so we save this code, run it again. Okay, we switch back and then we go to the analysis tab, scroll down to the last update here. So I think that is correct. Okay, I think 0C is the address of N1. We can double check that too. Okay, that has not changed. N1 is still at location FC, and then FE is the address of P first. How we know is we drew the map earlier. So now P first of main is updated to 0C, which is the correct thing. So I'm checking the code really statement by statement in C, and I'm not just kind of go like, oh, okay, assuming this is going to work, I'm going to move on and do the rest. Because otherwise it would be really, really hard to debug the program. All right, so this is working. So if I was using get, I would make another check-in because I got it working up to a certain point. It met all the expectations, you know, at least up to this point. All right, so now we move on to line 20. Okay, line 20 is pretty easy to do. Okay, because one is a parameter, the other one is a local variable. The way we access those particular items is kind of the same thing. So we just get the offset, get the address, get the value, and then move on to the left-hand side, offset, address, and then we do the store. Okay, so that means result should now be the same as ppn, and ppn is just p first, which is fe. So result should now be fe. So when we look at the map over here, oh, okay, I forgot to update this map here. So now we have the stack pointer pointing here because this is actually the result of f. And at this point, it should also be just the same as ppn, which is fe. So I forgot to do that part earlier. So which color is that? I think it's this one. Okay, so this is what we should be seeing is the update of location FE. Excuse me, is the location FA getting updated to the content or the value of FE. Okay, all right, so I always want to make sure that I know what the program is supposed to do by the time we get to this halt instruction. So we'll put a halt here and we say we should be seeing FA getting updated by FE as a content. Okay. All right. So we save again and then we run the code. So you can kind of imagine the difficulty of debugging programs for the early day mainframe programmers, because they cannot interactively run the program like this. They cannot just go like, I'm gonna make some changes and run the program again. Because guess what? The program is not in a text file. What do you think the program looks like? Punch cards. Punch cards. Yep. To change a program, you need to physically make new punch cards. And then you have to submit your deck of punch cards to the mainframe operator. And then the mainframe operator will go like, come back in a day. you right, you need to basically dry run the program in your head as much as possible before you turn it in. Okay, you cannot use an iterative debug process like what we are doing now. It is horrible. No, they're not. No, no, no. In the earlier days, okay, in the earlier days, programmers or developers, do not really get that big of a salary compared to other white collar jobs. Only the geekiest, nerdiest, most committed people would take on those careers because that's what they like to do. Exactly. Exactly. Yep. So no, there if you can look up the salary range, like how does it compare to other, jobs. I think those are jobs in the 60s ish. Okay, back in the 60s, we have really, really primitive tools for programming. So in the 60s, what is interesting is, um, I think all the way from the end of World War II, close to the 50s, all the way to maybe the 70s, you can make a good living just working at a fast food place. There is no need to become a programmer. You become a programmer only because that's your calling. Because otherwise, you can just work at a fast food place delivering fast food and retire from that job with a nice car and a nice house. Well, I mean, being able to collect, debt from a whole bunch of countries devastated in World War II allows that to happen. All right, cool. All right. So this is also why it is helpful to comment the whole instruction because you don't have to go like, okay, what am I supposed to see? Right there in the comment of the whole instruction. So this is good. So it's the technique, okay, that I'm talking about. All right, so we are good here. And that's pretty much the whole thing for the then branch, okay? And then we have to work out the else branch, okay? Because at some point the recursion has to happen, right? So we have to go to the recursive part, which is the else case. And now we work out the else case. Because for the then case, as far as we can test without testing this portion here, these three statements are now tested. Okay. Yep. Mm-hmm. Mm-hmm. That works too. Personally, I just like to preserve the ordering between the then versus the else case. So I want my assembly code, the positioning of the then versus the else, to match the C code. So this way, it's easier for me to track which branch am I on, which part am I working on, without having to remember. Oh, yeah, by the way, the assembly code has the else versus the then flipped. I like consistency because consistency means, you might end up wasting a few instructions, but what you're gaining is you don't have to kind of twist and turn in your head to remember, oh, wait, did I do the optimization and flip the two branches and this one is now the first and this one is now the second? If you add a lot of comments to remind yourself, you'll be fine. Yep, 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 yep. All right, so now we're down to line 24, which is the only recursion here. So the recursion is um, not super duper complicated. We'll start with the last argument, okay, which is just pn. Okay, that's the easy one. We'll work with that one first. So we'll do a LDI. Register is fine. F underscore pn add ad LDAA decrement d stda. So that would push pn on the stack. Okay, that's the easy peasy part. So the first argument looks super complicated, but it's actually easier than the one without the ampersand. Because in order to figure out the value of something, you have to figure out the address first. So the ampersand is just visually making it look more complicated than it really is. But you still have to figure out what it means. Okay. So we are looking at the address of the member called p next of a structure that is pointed to by a pointer that in return is pointed to by ppn. Okay, so you can write it out, you can draw a picture, Okay, whatever you do, you need to understand what you're dealing with. Okay, because then you can work on it one step at a time. So in this case, we load up register A is fine because we push it on the stack already. There's no need to save register A for whatever. So we do it as ppn, and then we add AD to get the address. We do LDAA to get to ppn itself. Um, and then we get to whatever it's pointing to, which is then a actual pointer to a struct node. And then we need another register to store the offset to the member called pnext. So that would be node underscore pnext. Add those two together, whichever order is fine because we don't need to save registers in this case because we're about to call a function. So because of the caller calling agreement, none of the registers is guaranteed to be the same when it returns. So no need to save anything now. Okay. So we add this, it becomes the actual address, and we are done. Okay, so now we just need to push register A on the stack, decrement D, stda, and then we can push the return address on the stack, which is LDIA. We typically use .6 plus. There are some variations to this, but this is the typical thing that we do, so we're going to stick with it for now. Push the return address, jmpi, to the function f. When it returns, we have the increment D, and that should be the whole thing. And then we store whatever return value into result. So we just have to do LDI B. I cannot use register A because it has the return value. So we do a LDI B with F underscore result, add BD, STBA. So that should, could do the whole thing. But I'm telling you, it is wrong. I can tell you that this is wrong. It has one little problem, and if we don't fix that problem, this whole thing is gonna go like it's gonna kill itself. So, what problem do we have? Well, let's go and put a halt instruction right here. Okay? In other words, we want to know what we're supposed to be seeing on the stack at this point. Okay? So according to this, we should be seeing pn on the stack. Okay? So we'll say pn. I'm trying to figure out how to specify that. Mm, So this will only happen in the second call. The first call would not trigger this code because we already know the first call is triggering this code. So the second call is going to trigger this code in the first invocation. So by that time, we know that pn is n2. So we know that pn is supposed to be n2. And we know that p first is pointing to n1. So that means the first argument. Okay, so we'll say the second argument. Second argument should be the address of n2. The first argument should be the address of n1's p next. Okay, so I want to see if that is actually being pushed on the stack, and by the time we get to the halt instruction. Because if I'm pushing the wrong stuff on the stack for the next function call, it's gonna blow up. Okay, so I already know what the problem is. Okay, but I want to show you a technique to find out what the problem is before it happens, before you kind of get the program to run into La La Land. Okay, so now we switch back. Okay, get to the halt instruction, and then we go like, okay, did we push the right stuff on the stack? Okay. All right, so we got to here, and we ask, what did we push on the stack? We pushed a df on the stack. So that would be p1 dot p next. Oh, that would be the address of n2. I don't think that is the address of n2. So hmm, in the F7 is 60. That is definitely wrong. The first argument is supposed to be wrong. So that one I don't have a problem with. Oh, wait, this is the return address. Never mind. Okay, that's my bad because I forgot about the return address. So this one is the first argument, which is definitely not the address of p next of p1, because when you go to the assemble tab, the next of p1 is right here. It's supposed to be 0c, and we are not pushing 0c on the stack. So now the question is, what did we push instead? And then we can also see the earlier code. It pushed the 0.8 on the stack here, and that is this is the problem of me not documenting my code. Okay, this is the else case. We're setting up the recursive call, and we are pushing pn on the stack. And pn, which is a pointer to a node, is 0.8. That cannot be correct. Oh, it is correct because it depends on which node we are pushing. So we are pushing n3 on the stack. So that 0.8 is fine. Okay, so that part works. And then the next argument that we are supposed to push is this one. It's pushing df on the stack, and that is definitely wrong. So the question is, why is it wrong? So this is ppn, okay, that's fine. It has an offset of 2, and then you add ad, add register D to register A, it is FB. So now the question is FB the correct location in the recursive call? So now we look into the stack space again. Okay, so we're looking at this location FB. That is definitely not PPN. It is one location below. And why is that? Because we pushed something already. Okay, so that's how we can figure this problem out is, before we let the function work, we just examine what is being pushed on the stack. We look at the parameters that we look at the arguments that we push. So the problem with this has to do with this decrement D here on line 88 is decreasing the stack pointer by 1. That means the stack pointer is now pointing to one location below the frame, the base of the frame. So, and because the assumption is f underscore ppn is the offset from the base of the frame to ppn, but the stack pointer is pointing to one location below that. So now we have to compensate. So the way we compensate for that is to put a 1 plus here. Okay, so that will fix that problem. And it's easier to rerun the code just the way it is, because the code would still work the same way, except by the time we get here, it would give me the correct location. It's now FC. We compare that to the map that we have, and FC is indeed the correct thing because we are supposed to retrieve PPN first. So that is correct now. All right. So now we know that part is working. We debugged. The most tricky part of this code here is probably that part. So now we can unlock this, actually do the recursive call, but then we also have to finish the whole thing, which means that by the time we get to end if, we have the return result. So now we have to do LDI f underscore result, add, oops, pick a register, add AD, LDAA. So that specifies the return value. And I think the whole thing should be done. This should conclude the whole thing. All right. So if assuming this is concluding the whole thing, how do we know whether it's working or not? I think I talked about this in class, what the C code is doing. P first points to a node, that node points to another node, that node points to another node. So that order should be preserved. Did I talk about that? Yeah, I cannot remember. We can yeah, we can just test it. Okay, so we'll go ahead and test the C code. So push D to here, GCC dash G dash O, AR.C, AR.AR.C. There we go, GDB AR, run, put a breakpoint on line 36. And then by the time we get there, we print what is P first. Oh, run P first. Okay, it is pointing to node 2. Then we print. Okay, this is going to be fun. Look at this. Look at this. This is going to be fun. What is the P next of this thing? Um, oh, and 3 because it's a chain. And then when you stack one more, it is the null pointer. All right. So this is what we're supposed to be seeing. Okay. So I'm just going to write it on the whiteboard because I won't remember that. So we know that P first points to N1, N2, and then N2, the P next of N2 points to N3, the P next of N3 points to N1, and then the P next of N1 points to a null. Okay, so we should expect the same structure in the assembly code. Okay, so even though the addresses are all different, but the structure of how things are linked should still be the same. Okay, so we take this, and then we do a pop D. This is really useful in Linux if you want to change directory, but you know that later on you have to go back to an earlier directory that you were in. You can do a push D, push directory, and then you can go back to the earlier one with pop D. Last in, first out in the command line interface. Huh? Yeah, yeah, but this is the shell. Yeah, if you use C shell, maybe it has a similar function, but I just like push D and pop D. It gives me the ability to switch to a different folder for a while and then come back to the earlier one. All right. So now we take a look at the trace, which is here. And the first thing we check is, did it terminate correctly? Yep, it did terminate correctly. Went back to the halt instruction. The stack pointer is null. Okay, so nothing is suspicious here. So now we can also take a look at the locations. Okay, so the way we debug this is we look at these locations here. So now what we should be seeing is at location 08, which is N3, it should contain the address of N2. So that means we should see an update of 0D getting the value of 0A. Okay, so that should happen during the execution at some point. Um, we should see P first pointing to N2, and we know that P first is location FE. So at some point, it should point to N2, and N2 is 0A. Um, wait, did I do this correctly? No, N3 points to N1. Okay, so I got that wrong. So N1 is at location 0C, so that means this is supposed to be a 0C. And then we know that N2 points to N2 points to N3. So that means this 0A should refer to 08. So 0A should refer to 08. And then N1 should point to null. So that means 0C should point to a null. So 0C should get 0, 0. So we are looking for these particular updates in the trace. Okay, so now we know what we are supposed to be looking for. We can now go back here and then just highlight the column of where we're supposed to find all that stuff. Go to edit, go to find and replace. Depending on how fancy you want your search to be, you can just do a regular search without using regular expression. So we know 0A is supposed to get 08, right? Yep. So find, okay, found it. We know that 08 is supposed to get 0C. So 08 is supposed to get 0C. Yep, we got that. We know 0FE is supposed to get 0A. Okay, it will be updated several times. Okay, but the last one should be that. So we're looking at FE getting 0C. Okay, we got that. Oh, 0A, sorry. Here we go. So that's pretty close to the end if you look at the row number. And then finally, we are looking for 0C getting 00. So that one may or may not happen. I think it should happen. Yep, it did happen too. So now we have all the updates that we're looking for. Everything is good. So that's kind of how I would debug this program. Are there any questions about the whole process? Oh, did the program work? Backwards. Well, if it is consistently backward, no, it still won't work because main is going to call it with in the correct order. Yep. All right. Any questions about this? Nope. Okay. So we still have about 15 minutes. Um, do you want another practice that I'm not going to grade? You do? Okay. All right. We can do another practice. I suppose we can use this one. I haven't touched it for a long time, so I don't know exactly what it is. All right. So we do a. Okay. All right. So this is the C code. Oh, I like this one. This is a traversal kind of programming. All right. So we have, node again, but this time we have two pointers in each node. So each node has a left pointer and a right pointer, and it has a value. All right, so the way this one works is the best way to visualize is to see it as quote unquote a tree. If you have not taken CISP 430, it's okay. I will still explain it. So the root node is N1. N1 is what we call the root node, which means you can think of it as the starting point. So here we have N1, and N1 has a few items. Okay, first of all, it has a value. So N1 has a value of 5. Okay, so we say that N1 has a value of 5, and then it has two pointers. It has a left pointer and a right pointer. The left pointer points to N2, so this one goes to N2. So we just name the thing. N2 has a value of 3, and it has a null pointer for its left, but the right pointer is N4. So this points to N4. So here's N4. N4 has a value of 3. Nope, it has a value of 10. Nope, 4. Okay, excuse me. Okay, that's a 4 and has null pointer and also null pointer here. Are we good? And then when you look at the right of N1, it points to N3. N3 has a value of 10. The left points to N5. which has a value of 9, and then that has no pointers for both its left and right, and then the right pointer of n3 is a null. Okay, so first of all, I'll be okay with that picture. So what the algorithm does, okay, when you look at traverse, hmm, say again, extern. So extern is just a way to say that, yeah, don't nag me because you have not seen N2 yet. It will be defined later. It gives the compiler it let the compiler knows that this is a forward reference and I will give you N2 at some point. So it doesn't complain. Yeah. Yep. Because without the extern it would just kind of complain and go like, "Hey, you don't have extern you don't have N2 defined yet. I don't know what N2 is on line 25." Yep. Yeah, yeah, yeah. Basically, C and C++ has a lot of ways for you to say, "I know what I'm doing. Shut up." This is one of those. Okay. No, it's not a linker problem. This is strictly a compile time problem. So you can, okay, if I take this out, okay, it will complain on line 25 and say that N2 is not defined at that point. So we'll do gcc-g-o struct.c, and you can see how it's complaining. Hey, I don't know this. Do you mean N1? Because N1 is the only struct node defined at that point. So it would actually give you a suggestion, which is wrong in this case. So does that answer your question? Yep. Okay. So extern basically just means that it will be defined. This is the type of that thing when it is defined. So stop complaining about it. Yep. 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 So the recursive call traverse is going to quote unquote traverse the left hand side first. When the entire left-hand side is done, and then it's going to do some stuff over here in between the two traverses, and then it will traverse the right-hand side. So the ordering of traversing in this case is we start with M1, it goes to the left-hand side, there's no left-hand side at this point, goes back to, nope, I take it back. It would give you the 3, and then go to the right-hand side, then it would try to go to the left-hand side, there's nothing there, give you the 4, it will try to go to the right hand side. There's nothing there. And then we'll backtrack. And then we'll backtrack to here. And then go to the right hand side. And then we'll print the 5. And then go onto this side. And then we'll attempt to go to the left hand side, which there's something here. Then we'll try to go to the left hand side of this thing. There's nothing there. Goes back, print the 9. Try to go to the right hand side. Nothing there. Go back to N5. Go back to N3. Print the 10. Try to traverse the right hand side. Nothing over there. Go back to N1. Done. So that means the ordering of what it writes to array would be the same order in the sort. It would be the sorted order of the values. It would basically do a 3, 4, 5, 9, and 10. That's the that would that those are the values stored in array in the global array, not the global, but in the local variable array sorted in main. Yep, yep. What do you mean by anything? No, this is what we call a binary search tree. So in a binary search tree, whatever is to the left-hand side of a particular node, they all have values that are less than that node. And all the values on whatever the right-hand side is should be all greater than the value of the node, of the value of the node itself. So it's called a binary search tree, which is a concept in CISP 430. So this is an algorithm that they will talk about in CISP 430, the data structure class. But I'm not asking you to derive the algorithm. I'm asking you to translate the code into assembly code. Yep. So, but just to illustrate what it does, okay, so we'll go ahead and take a look at what it actually does. So we'll do a GCC, recompile the code, struct.c, gdb struct, and then put a breakpoint on, put a breakpoint on line 34, like so. Stop here, and I will intentionally put stuff into sorted, okay? So I will say uh, set var sorted bracket 0. We'll give it some values that are not even in the nodes. So this way we know when it is initialized, okay, or when it gets a value. We'll say, well, okay, I'll do something even better. I'll set up watch points, okay. So watch points are really cool, but I'm not sure whether it can watch the entire array. We'll give it a try. Cool. Looks like it accepted that, but I'm not sure whether it's just watching the first location of sorted or the actual entire array. Okay, so we'll find out soon. All right, so we run the code from the beginning. Okay, that's where we put the breakpoint. Okay, cool, not a problem. And it does not stop when we write to sorted. Okay, that didn't work. So now we have to delete the watch point. So we'll delete watch point 2. No, delete. How do I delete watch points? Delete watch 2. There we go. And we can now select each one location. We can say sorted 0. Oh, I have to run the code first. Okay, watch sorted 0, 1, 2. I don't know how many we can set up, but okay, we can watch all of them. Okay, so the watch feature of GDB is really kind of cool because it says every time if any one of these elements got changed, it will stop the execution of the program and tell you about the update. This was the value. This is the new value. Okay, so it's really kind of helpful that way. So we'll go ahead and run the code again. Okay, we'll continue execution. Oh, okay, it won't do it. It won't do it. Ah, okay. You have requested too many hardware breakpoints. It doesn't like it. Darn. Okay. All right, fine. We'll go ahead and quit, do the whole thing again, but this time we just run it to the end and then we print sorted to see what's in it. So list again, put a breakpoint on line 36, run the whole thing, print sorted. So we can see that it has 3, 4, 5. This is the tab character, which is 9, and this is the line feed character, which is 10. So it basically traversed the tree here, and it would go like, okay, traverse the left-hand side, try to traverse the left-hand side, nothing there, put the 3 into the array. Traverse the right-hand side, go to the 4, try to traverse the left-hand side, nothing, come back, print the 4, put the 4 into the array, try to traverse the right-hand side, nothing, go back to the previous one, go back to the previous one, put the 5 into the array, traverse the right-hand side, try to traverse the left-hand side, try to traverse the left-hand side, nothing there, come back, print the 9, try to traverse the right-hand side, nothing there, come back, put the 10 into the array, try to traverse the right-hand side, nothing there, come back, and the algorithm is done. So it's a recursive algorithm, um, and it is one of the I would say one of the easiest recursive structure in data structure. Because when you look at a node, any node, when you look at a single node, it is by itself a binary search tree. It is just a very deformed binary search tree with only one single node. When you look at this portion or the sub portion here, it is also a binary search tree. When you look at this entire thing, it is also a binary search tree. So any part of the binary search tree is by itself a binary search tree. So if you know how to print things in the correct order with a binary search tree, then you can recursively do the same thing and print out the entire binary search tree in the correct order. So this is something, how many people have taken 430 at this point? Hmm? Yeah, this class only has a prereq of 360. The order of the dependency is P300 is required for P360. And once you have P360, you can do both at the same time. So that would be this class, P310, and then P400. But then you need P400 to get to P430. And then P440 is a little bit on the weird side because it's a co-requisite. So this one can go along with P440. So that's kind of the dependency hierarchy of the classes. Yes. After this class, you cannot take 440 unless you have taken 400. Yeah, because 400 is what you need to get to P430, and the 430 is a co-requisite of 440. So that means you can take them in the same semester if you want to, but you can also take 430 first, then you take 440 later. But they can be taken in the same semester because it's a co-requisite. Yep. All right. So we are running out of time today. So if this is the kind of challenge that you want to take on, at least give it a try. Okay, I'm not gonna grade this particular one. I can I can unhide the file over here, so we can just go back to. Oh, okay. Yeah, just let it be open. There's no need for password. Mm, where is it? This one here. I might as well also open the other one too. Un So we want to publish this. Yes. And I'll also open this up too. If you're curious, I would do the L list first, because it's just a linked list. It's not quite as bad as having 2 points of recursion. So if I were you, I would kind of look at L list first and then take a look at struct. So I would do the C code. I think the assembly code is already done. So for this one, that's why I'm not going to grade it because it's already done and you have the solution. So let me just double check. Nope, it's not done. Which is good. Okay, if it's not done, it means I can do it in one of the classes. So we have the final exam on the 17th. Okay, so that means on the 10th, which is next Wednesday, we'll have a review of the final exam. So that means next Monday, we can take a look at Traverse or L-List. Okay, you guys can pick either one and we can go over the solution to that one. And I think it's beneficial because it's kind of the same thing, kind of just remixed a little bit. All right. So I don't have a lab for you guys today because all the basic knowledge is already done. So I don't have a lab. So if you want to work on either, struct or list, during the lab time, you're welcome to. If you want to work on those later on, someplace else, that's okay with me too. If you want to work on the final exam, which I think I have given you a copy of, right? So if you want to work on that at this time and you want to ask me questions about it, we're all good with that too. So I'm gonna stay here for as long as you guys are here, and I will be able to answer questions. Okay. So let me stop the recorder.